According to the National Electrical Code, it is permissible to run both low-voltage lighting and sprinkler valve wires in the same conduit, provided that certain conditions are met. Firstly, conduit size is important. The conduit must be large enough to accommodate all of the conductors, with a minimum fill of 40%. In this specific case, a 1-inch conduit is suitable. Secondly, voltage rating is important. The conduit must have a voltage rating equal to or greater than the highest voltage of any conductor inside it. Given that the lighting conductors are rated for 600 volts, the conduit must also be rated for 600 volts or higher. Thirdly, insulation is crucial. All conductors must be properly insulated for the voltage they are carrying. The lighting conductors, rated for 600 volts, must be insulated for at least 600 volts. Conversely, the sprinkler valve wire, rated for 30 volts, requires insulation of at least 30 volts. Fourthly, separation is necessary. The conductors must be separated from each other by a barrier. This could be a plastic divider or a layer of tape. The purpose is to prevent the conductors from touching and causing a short circuit. Fifthly, grounding is also necessary. All metal conduits must be properly grounded. This measure protects against electrical shock in the event of a fault. In summary, the conditions necessary to run the wiring in one conduit include the correct size of conduit so that the conductors are not overcrowded, using conduit that has a voltage rating at least as high as the wires installed in it, using insulated wires that are rated for the voltage of the wires themselves, using a divider or tape wrap to keep them separate from each other, and, finally, ensuring that the conduit is properly grounded to prevent electrical shock. Using the correct size of conduit, the NEC specifies fill rates so that the conduit is not overcrowded. NEC Section 314.16 covers the requirements for the number of conductors in outlet device and junction boxes and conduit bodies. These regulations are designed to prevent overheating and to allow for sufficient space to make connections. To determine the correct size of conduit, firstly, determine the total cross-sectional area of all conductors including their insulation. You will need to consult the tables in Chapter 9 of the NEC to obtain the dimensions of the conductors you intend to use. Secondly, select the appropriate conduit type. Different types of conduit have different fill limitations. Commonly used conduits include electrical metallic tubing, intermediate metallic conduit, rigid metal conduit, and rigid polyvinyl chloride conduit. Thirdly, consult the conduit fill tables in Chapter 9 of the NEC. These tables specify the maximum percentage of conduit cross-sectional area that can be occupied by conductors. The allowable fill percentages vary based on the number of conductors in the conduit. For example, for 3 or more conductors, the fill is generally limited to 40%. Fourthly, calculate the maximum allowable conductor area. Multiply the cross-sectional area of the conduit by the allowable fill percentage to determine the maximum area available for conductors. Fifthly, compare the total conductor area to the maximum allowable conductor area. The total cross-sectional area of all conductors must be less than or equal to the maximum allowable conductor area for the selected conduit size. If the total conductor area exceeds the maximum allowable area, a larger conduit size is required. For example, suppose you need to run 4 number 12 AWG-THHN conductors in a conduit. From NEC Table 5 in Chapter 9, the cross-sectional area of a number 12 AWG-THHN conductor is 0.133 square inches. The total conductor area would be 4 multiplied by 0.133, which equals 0.532 square inches. For more than 2 conductors, the allowable fill is 40%. From NEC Table 4 in Chapter 9, the cross-sectional area of a 1/2 inch EMT conduit is 0.304 square inches. The maximum allowable conductor area in a 1/2 inch EMT conduit is 0.4 multiplied by 0.304, which equals 0.1216 square inches. Since the total conductor area of 0.532 square inches is less than the maximum allowable area of 0.1216 square inches, a 1/2 inch EMT conduit is sufficient for this application. In some cases, derating of the wire size may be required. NEC Section 310.15 addresses the requirements for ampacity of conductors. Ampacity refers to the current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The NEC provides tables that list the allowable ampacities for various conductor types and sizes under specific conditions. These ampacity values are based on factors such as conductor material, insulation type, ambient temperature, and the number of current carrying conductors in a raceway or cable. Adjustments to ampacity may be required under certain conditions. Firstly, ambient temperature correction is needed. The ampacity tables in the NEC are based on a specific ambient temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the actual ambient temperature exceeds this value, the ampacity of the conductor must be reduced to prevent overheating. Correction factors are provided in NEC tables to adjust the ampacity based on the actual ambient temperature. Secondly, conductor dirting is needed. When multiple current carrying conductors are installed in a raceway, cable, or bundle, the heat generated by each conductor can raise the overall temperature and reduce the ampacity of the conductors. To address this, the NEC requires that the ampacity of the conductors be derited based on the number of current carrying conductors. Deriting factors are provided in the NEC tables to adjust the ampacity based on the number of conductors. Thirdly, voltage drop is something to consider. While not strictly a deriting factor, voltage drop can impact the performance of electrical equipment and systems. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. If the voltage drop exceeds these limits, the conductor size must be increased to reduce the voltage drop and ensure proper equipment operation. To determine if deriting is required, firstly, determine the allowable ampacity of the conductor from the NEC tables based on its size, insulation type, and temperature rating. Secondly, determine the ambient temperature and apply any necessary correction factors from the NEC tables. Thirdly, count the number of current carrying conductors in the raceway, cable, or bundle. Fourthly, apply the appropriate deriting factors from the NEC tables based on the number of current carrying conductors. Fifthly, compare the adjusted ampacity to the load current. The adjusted ampacity of the conductor after applying all correction and deriting factors must be equal to or greater than the load current. If the adjusted ampacity is less than the load current, a larger conductor size must be used. For example, suppose you have three number 12 AWGTHHN conductors carrying a load current of 20 amps in a raceway with an ambient temperature of 40 degrees Celsius. From NEC Table 310.15b16, the allowable ampacity of a number 12 AWGTHHN conductor is 30 amps at an ambient temperature of 30 degrees Celsius. From NEC Table 310.15b2, the correction factor for an ambient temperature of 40 degrees Celsius is 0.88. The adjusted ampacity for ambient temperature is 30 amps multiplied by 0.88, which equals 26.4 amps. From NEC Table 310.15b3, the deriting factor for three current carrying conductors in a raceway is 0.80. The adjusted ampacity for conductor deriting is 26.4 amps multiplied by 0.80, which equals 21.12 amps. Since the adjusted ampacity of 21.12 amps is greater than the load current of 20 amps, deriting is not required in this case. Proper wire insulation is important for electrical safety. The National Electrical Code specifies insulation requirements. Here are some key points to keep in mind. Firstly, voltage rating is important. Select conductors with an insulation voltage rating equal to or greater than the circuit voltage. This ensures that the insulation can withstand the electrical stress without breaking down. Secondly, insulation type is important. Choose the appropriate insulation type based on the application and environmental conditions. Common insulation types include THHN, THWN, XHHW, and others. Each type has different temperature ratings, moisture resistance, and other characteristics. Thirdly, conductor size is important. Ensure that the conductor size is adequate for the circuit's ampacity and voltage drop requirements. The NEC provides tables that specify the allowable ampacities for various conductor sizes based on insulation type and temperature rating. Fourthly, environmental conditions are important. Consider the environmental conditions in which the conductors will be installed, such as temperature, moisture, chemicals, and sunlight exposure. Select insulation materials that are suitable for these conditions. Fifthly, listing and labeling are important. Use conductors that are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories. This ensures that the conductors meet industry standards for safety and performance. Sixthly, proper installation is important. Install conductors according to the manufacturer's instructions and the requirements of the NEC. Avoid damaging the insulation during installation and ensure that connections are made properly. Some common insulation types include THHN, which stands for thermoplastic high heat resistant nylon coated. THHN is a common general purpose wiring. It is suitable for dry locations and has a temperature rating of 90 degrees Celsius or 194 degrees Fahrenheit. Another type is THWN, which stands for thermoplastic heat and water resistant nylon coated. THWN is similar to THHN but is also suitable for wet locations. It also has a temperature rating of 90 degrees Celsius or 194 degrees Fahrenheit in dry locations and 75 degrees Celsius or 167 degrees Fahrenheit in wet locations. Another type is XHHW, which stands for cross-linked polyethylene high heat and water resistant. XHHW has excellent moisture resistance and is suitable for both wet and dry locations. It has a temperature rating of 90 degrees Celsius or 194 degrees Fahrenheit in both wet and dry locations. And another type is UF, which stands for underground feeder. UF cable is designed for direct burial in the ground. It has a moisture-resistant insulation and a temperature rating of 75 degrees Celsius or 167 degrees Fahrenheit. Grounding is a critical safety measure in electrical systems. It provides a low impedance path for fault current to flow back to the source, which helps to quickly trip a circuit breaker or fuse and energize the circuit. This reduces the risk of electrical shock and fire. Here's a breakdown of key grounding concepts. Firstly, grounding electrode system is important. The grounding electrode system consists of one or more grounding electrodes that are connected to the earth. Common grounding electrodes include metal underground water pipes, ground rods, and ground plates. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage and provide a path for fault current to flow. Secondly, equipment grounding conductor is important. The equipment grounding conductor provides a low impedance path for fault current to flow from non-current carrying metal parts of equipment back to the source. This helps to quickly trip a circuit breaker or fuse in the event of a fault. The equipment grounding conductor is typically a green or bare copper wire that is run along with the circuit conductors. Thirdly, bonding is important. Bonding is the process of connecting together all non-current carrying metal parts of an electrical system to create a continuous electrical path. This helps to ensure that all metal parts are at the same potential, which reduces the risk of electrical shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that are used to connect metal parts together. Fourthly, ground fault circuit interrupter protection is important. Ground fault circuit interrupters are devices that are designed to protect people from electrical shock. They work by monitoring the current flowing in a circuit and quickly tripping the circuit breaker if a ground fault is detected. Ground fault circuit interrupters are required in many locations such as bathrooms, kitchens, and outdoor areas. Fifthly, grounding and bonding of metal conduits is important. Metal conduits such as EMT and rigid metal conduit must be properly grounded and bonded to ensure electrical safety. This helps to provide a low impedance path for fault current to flow back to the source in the event of a fault. Grounding and bonding of metal conduits is typically accomplished by using grounding bushings and bonding jumpers. According to the NEC, the size of the grounding electrode conductor depends on the size of the service entrance conductors. For example, for a service entrance conductor size of 2/0 AWG copper or 4/0 AWG aluminum, the minimum size of the grounding electrode conductor is number 4 AWG copper or number 2 AWG aluminum. For a service entrance conductor size of 3/0 AWG to 350 kcmil copper or 250 kcmil to 500 kcmil aluminum, the minimum size of the grounding electrode conductor is number 2 AWG copper or number 1/0 AWG aluminum. For a service entrance conductor size of over 350 kcmil to 600 kcmil copper or over 500 kcmil to 900 kcmil aluminum, the minimum size of the grounding electrode conductor is number 1/0 AWG copper or number 3/0 AWG aluminum. And for a service entrance conductor size of over 600 kcmil copper or over 900 kcmil aluminum, the minimum size of the grounding electrode conductor is number 3/0 AWG copper or number 250 kcmil aluminum. The equipment grounding conductor size is based on the overcurrent protective device. According to NEC Table 250.122, for an overcurrent protective device rating of 15 amps, the minimum size of the equipment grounding conductor is number 14 AWG copper or number 12 AWG aluminum. For an overcurrent protective device rating of 20 amps, the minimum size of the equipment grounding conductor is number 12 AWG copper or number 10 AWG aluminum. For an overcurrent protective device rating of 30 amps, the minimum size of the equipment grounding conductor is number 10 AWG copper or number 8 AWG aluminum. For an overcurrent protective device rating of 40 amps, the minimum size of the equipment grounding conductor is number 10 AWG copper or number 8 AWG aluminum. For an overcurrent protective device rating of 60 amps, the minimum size of the equipment grounding conductor is number 10 AWG copper or number 8 AWG aluminum. For an overcurrent protective device rating of 100 amps, the minimum size of the equipment grounding conductor is number 8 AWG copper or number 6 AWG aluminum. For an overcurrent protective device rating of 200 amps, the minimum size of the equipment grounding conductor is number 6 AWG copper or number 4 AWG aluminum. For an overcurrent protective device rating of 300 amps, the minimum size of the equipment grounding conductor is number 4 AWG copper or number 2 AWG aluminum. And for an overcurrent protective device rating of 400 amps, the minimum size of the equipment grounding conductor is number 3 AWG copper or number 1 AWG aluminum.